Hello, grade 10s. Welcome back to another lesson of mechanics, and we're going to continue with motion in one dimension. And today we are going to start on motion graphs. We're going to learn how to draw them, how to analyze them, how to describe them. So now that we understand the definitions of distance, displacement, speed and velocity, and acceleration, we may use these ideas to describe how an object moves and represent that using graphs. And we're going to consider three types of motion. Scenario 1 applies to an object that is stationary or not moving. Scenario 2 applies to motion that is uniform. That means that the object moves with a constant velocity. A constant velocity also means a constant change in displacement. So the displacement changes by the same amount every second, and that creates a constant velocity. And scenario 3 applies to constant acceleration. A constant acceleration means that the object moves with a constant change in velocity. So every second, the velocity will either speed up or slow down by the same amount. So let's start off with the simplest scenario, which is scenario 1, a stationary object, an object that is not moving. So the simplest motion is that of a stationary object. It doesn't move, so that means that its position doesn't change with time. Let's consider this scenario. Tammy waits for her mom to pick her up from school. Street is the point of reference, and she's standing 2 meters away from the stop street in the positive direction at 0 seconds. After 1 minute, which is at 60 seconds, she's still standing 2 meters away from the stop street in the positive direction. And after 2 minutes, which is 120 seconds, she's still standing 2 meters away from the stop street in the positive direction. So her position over the 2 minutes doesn't change. So that means that her displacement, which is change in position, is 0. And because her displacement is 0, meaning that she hasn't changed her position, meaning that she hasn't moved, her velocity is 0. And when there's no velocity, there's no acceleration. So her acceleration is also 0. So now we may draw corresponding graphs for this motion. We have a position time graph, a velocity time graph, and an acceleration time graph to represent the scenario, which is Tammy standing 2 meters away from the stop street in the positive direction for 120 seconds. Time always goes on the x-axis, and you'll notice that the three x-axes over here in my position time, velocity time, and my acceleration time graphs are identical. That's because for this particular motion, the time hasn't changed. Tammy is standing at the stop street for 120 seconds. But now we need to consider the position time graph, velocity time graph, and acceleration time graph. So in terms of the position time graph, Tammy's standing 2 meters away from the point of reference, which is here, in the positive direction. Hence, it is in the first quadrant for 120 seconds. So at time 0, she's 2 meters away from the stop street. After 60 seconds, she's still 2 meters away from the stop street. And after 120 seconds, she's still 2 meters away from the stop street. This line over here does not need to be shown, but sometimes it just helps us to align the end of the time interval with a graph line. Now, as far as the velocity time graph is concerned, well, if there's no change in position, there's no velocity. So for 120 seconds, Tammy had no velocity. And if there's no velocity, there's no acceleration. So for 120 seconds, Tammy had no acceleration. Let's now start describing these graphs. So what does this x versus t graph show us? Well, it shows us that Tammy's position is 2 meters away from the origin. We always assume that the 0 point is the origin unless otherwise stated. In the positive direction, because this is a positive 2, for 120 seconds. What does the v versus t graph show us? Well, it shows us that Tammy has no velocity for 120 seconds, and the a versus t graph shows us that Tammy had no acceleration for 120 seconds. Now, we need to recall from maths that the gradient m of a graph can be calculated by dividing the change in y, delta y, over the change in x, delta x. So it's the dependent variable divided by the independent variable. So mathematically, m, which is the gradient, is equal to delta y over delta x. Now the gradient of an x versus t graph is always going to represent velocity, because velocity is the rate of change in position based on a position time graph. The gradient v will be the change in position over the change in time. Now we're going to bank the next 2 points because they apply to scenario 2 and scenario 3, and we are currently discussing scenario 1 for a stationary object. But in the case of a constant velocity, which we'll come to in scenario 2, the gradient of an x versus t graph represents average velocity. And in the case of a constant change in velocity or constant acceleration that we'll discuss in scenario 3, the tangent of an x versus t graph represents the instantaneous velocity. We're going to come back to that. It's going to make a lot more sense later. But what we do need to take away from this now is that the gradient of an x versus t graph represents velocity. What about the gradient of a v versus t graph? Well, we need to know that the gradient of a v versus t graph represents acceleration, because acceleration is the rate of change in velocity. Now, we only deal with constant acceleration, so that means that average acceleration and instantaneous acceleration will always be the same. But we haven't learned the difference between average versus instantaneous types of motion. So again, if you find this a little bit confusing, that part will make sense a little bit later. Now, let's calculate Tammy's velocity by considering the gradient of an x versus t graph. We can see that here the gradient is 0. It's a flat line, which is why if we had to calculate velocity, we would find that the velocity is 0, which then translates correctly to this graph. Let's take a look. So we don't say m equals delta y over delta x in science, because remember that science is an applied maths. So in this case, our gradient is actually the velocity, and the delta y is the change in position, because position is represented on the y-axis, and the delta t is the change in time, because time is represented on the x-axis. So remember, change in anything is final minus initial. So it is xf minus xi over tf minus ti. Now, Tammy's final position at the end of the time interval was 2 meters, and Tammy's initial position at the start of the time interval was also 2 meters. Both of them are positive because both of them are in the positive direction. So it's plus 2 minus plus 2. So it's 2 minus 2 over final time, which is 120 seconds, minus initial time, which is 0 seconds. So that obviously gives us an answer of 0 meters per second. And that makes sense because if you're standing still, you have 0 velocity. The flat gradient of an x versus t graph is going to represent zero velocity. Now, you wouldn't generally be asked to calculate a flat gradient. So you just need to know that a flat gradient of an x versus t graph will represent zero velocity. And in the same way, we're going to see that a flat gradient of a v versus t graph will represent zero acceleration. So next, let's do that. Let's calculate Tammy's acceleration by considering the v versus t graph. Now again, the gradient of a v versus t graph will give us the value of the acceleration. So we say that acceleration, which is the gradient, m, is equal to delta v over delta t, which is the same as delta y, because velocity is on the y-axis, over delta t, because time is on the x-axis. Change in anything is final minus initial. So that is equal to Vf minus Vi over Tf minus Ti. Now, Tammy's final velocity is 0 meters per second and her initial velocity is 0 meters per second. Her final time is 120 seconds and her initial time is 0 seconds. So that gives us an acceleration of 0 meters per second squared, which then translates into this graph over here. So the flat gradient of a v versus t graph will represent zero acceleration. So in summary, the gradient of an x versus t graph represents velocity. The gradient of a v versus t graph represents acceleration. Two other important points that we need to note. The area under a velocity time graph, which in this case there is no area under the velocity time graph. It represents displacement or change in position. In Tammy's case, there's no area under the v versus t graph, so that's then clear that there is zero displacement. She hasn't changed her position. She stood in the same spot for 120 seconds. The other important thing that we need to consider is that the area under an acceleration time graph will represent velocity. Now, again, here we don't have area under the acceleration time graph. So in this case, that means zero velocity. But we'll come back to these calculations later when they become more relevant. Now that brings us to scenario 2, which is uniform motion. Uniform motion means that the object moves at a constant velocity. It also means that the object moves with a constant change in displacement. So a constant change in displacement means a constant velocity. And a constant change in displacement means that the position of the object is changing by the same amount every second. So it is changing at the same rate. In the morning, Tammy walks from her home to the bus stop, which is 100 meters away from her home. And it takes her 100 seconds to walk from her home to the bus stop. And here we can see a diagram of Tammy's position. So what we can see is that after 50 seconds, she's covered 50 meters, and after 100 seconds, she's covered 100 meters. So essentially what that means is that she's traveling at 1 meter per second, which means that after 1 second, she's covered 1 meter. After 2 seconds, she's covered 2 meters. After 3 seconds, she's covered 3 meters, etc. So you can see what it means when we say that the position of the object is changing at the same rate. It's changing by the same number of meters every second. So now we can draw our position time, velocity time, and acceleration time graphs for Tammy's motion. We're going to assume that the origin is Tammy's house and towards the bus stop is the positive direction. So Tammy's change in displacement or position shows that she walks 1 meter in the first second, another meter in the second. After 50 seconds, she's covered 50 meters. And so we can see that her position, her displacement, is increased by 1 meter away from the point of origin every second. So the position time graph for this motion will look like this. So that at time 0, her position is 0. And at exactly 50 seconds, her position is 50 meters. And at 100 seconds, her position is 100 meters. What does this x versus t graph represent? It shows us that Tammy walks with a constant change in position in the positive direction because the graph has a positive gradient for 100 seconds. Now that we've described the x versus t graph, and an x versus t graph is a position or displacement time graph, so when we describe it, we have to describe it from the perspective of change in position. Let's now calculate Tammy's velocity, and then we can describe the velocity time graph. Now, the xt, vt, and at graph all represent the exact same motion, but there might be some subtle differences in the way that we describe the motion from the perspective of position versus velocity versus acceleration. So remember that the gradient of the v versus t graph represents velocity. What we have here is a single gradient graph. So we've got v, which is equal to delta x, represented by the y-axis, over delta t, represented by the x-axis. Now, I, in my calculation, have used the full right angle triangle here, but you can use any right angle triangle and just read the values off the graph. It's just ratio, so you're always going to get the same answer. Tammy's final position is 100 meters, and her initial position was at her home, which was the reference point, which is 0 meters. So it is 100 minus 1 over her final time, which was 100 seconds, minus her starting time, which was 0 seconds. And so that gives us an answer of 1 meter per second. Remember, it's a vector, so we have to state direction. It's in the positive direction, which is why we got a positive answer. And we know that the positive direction is towards the bus stop. So Tammy traveled at 1 meter per second towards the bus stop. Tammy's velocity is positive because she walked in the positive direction. The fact that the x versus t graph has a single gradient means that Tammy's velocity is constant. It is the same at any point in time during her motion. The fact that the x versus t graph has a positive gradient means that Tammy walked in the positive direction. So now that we know that Tammy's velocity is 1 meter per second towards the bus stop for 100 seconds, we may draw the corresponding v versus t graph. The velocity time graph is going to look like this. For the 100 seconds of motion, Tammy's velocity was constant at 1 meter per second. Let's now the motion of the graph from the perspective of the velocity time graph. And we can see that Tammy travels at a constant velocity of 1 meter per second towards the bus stop, which is the positive direction, for 100 seconds. Now, because Tammy's velocity is constant, is Tammy accelerating? Well, if your velocity is constant, it means that you are walking at a steady speed. You're not speeding up and you're not slowing down. So your acceleration must be 0. So acceleration, which is the rate of change of velocity, is 0 when the velocity is constant. Recall that the gradient of a velocity time graph represents acceleration. And here we have no gradient. Therefore, it represents 0 acceleration. So Tammy's acceleration is 0 meters per second squared for the 100 seconds, which we may represent on this acceleration time graph, where for the 100 seconds, Tammy's acceleration is 0. Now, let's go back to our velocity time graph, where Tammy walked for 100 seconds at 1 meter per second. Now, if we calculate the area under the velocity time graph, then we will be able to work out Tammy's displacement. How many meters has Tammy covered? Mathematically, that's because velocity is position divided by time. So we may rearrange this formula to say that position is velocity times time. Remember that the formula for the area of a square or rectangle is length times breadth. So if we consider this velocity time graph, the length is represented by time and the breadth is represented by velocity. So multiplying the two together will give us Tammy's change in position. So let's calculate Tammy's displacement from this V versus T graph. So x equals V times T, which is equal to 1 times 100, which is equal to 100 meters. We got a positive answer, meaning that the direction's positive, which is towards the bus stop. And we know based on the scenario that Tammy did indeed walk 100 meters towards the bus stop, but now we've proven it by calculating the area under the velocity time graph. Now, after school, Tammy walks 100 meters now in the opposite direction, so from the bus stop to her house. She's going to be walking at the same rate, but the direction of the bus stop is still the positive direction. So now she's going to be walking in the negative direction. So the position versus time graph for this motion looks like this. Now what we can see is that at time 0, Tammy was 100 meters away from the reference point, which is her house. And then she's now walking in the negative direction towards her house. So after 50 seconds, she is 50 meters away from her house. But we have a negative gradient because she's walking in the negative direction. After 100 seconds, she is at position 0, which is the reference point, which is her house. So what does the x versus t graph represent? Well, it shows us that Tammy walks with a constant change in position in the negative direction, which is towards her house, for 100 seconds. Now, let's calculate Tammy's velocity, and remember that the gradient of an x versus t graph represents velocity. But also note that here we have a negative gradient. So we're expecting to calculate a negative velocity. A negative velocity means in the negative direction. So V equals delta x over delta t, which is xf minus xi over tf minus ti. Now, in this case, Tammy's final position was here at her house, and Tammy's initial position was 100 meters away from her house in the positive direction, so it's plus 100. So xf minus xi is represented by 0 minus 100. Time is 100 minus 0. As I already mentioned before, time can never be negative. So we end up with an answer of minus 1. And that means 1 meter per second in the negative direction, which in this case is towards Tammy's house. Tammy's velocity is negative because she walked in the negative direction. The fact that the x versus t graph has a single gradient means that Tammy's velocity is constant, and the fact that it has a negative gradient means that Tammy is walking in the negative direction. Now that we know that Tammy's velocity is 1 meter per second towards her house, which is in the negative direction, we may draw the v versus t graph. And what we need to note is that in this case, the velocity is graphed in the fourth quadrant at the point of -1, because her velocity is 1 meter per second in the negative direction. So when velocity is negative, it is graphed in the fourth quadrant. When it is positive, we graph it in quadrant 1, and when it is negative, we graph it in quadrant 4. What does this v versus t graph represent? Well, it shows us that Tammy travels at a constant velocity of 1 meter per second towards her house for 100 seconds. And because Tammy's velocity is constant, is Tammy accelerating? The answer is no. Acceleration is the rate of change of velocity. The velocity is constant, so there is zero acceleration. So if we had to graph Tammy's acceleration, which is 0 meters per second squared for 100 seconds, then we get this graph, which represents zero acceleration for 100 seconds. Now let's go back to the v versus t graph where Tammy walks back home, and recall that the area under a v versus t graph represents displacement, and let's calculate Tammy's displacement. So remember that the change in position or displacement, we can calculate it as velocity times time, and in this case velocity is -1 and time is still 100. And that gives us an answer of -100, which means 100 meters in the negative direction. And the negative direction is towards Tammy's house. That brings us to scenario 3, which is motion with a constant acceleration. And we will start here in the next lesson.